Hi, everybody. Welcome to the AI Research School. So today we have a talk on application of visual data. So this is with us here today. We have Dr. Gangizadeh. Sorry if I said your name wrong, but
That's
yeah.
that's correct.
So Ali is a medical graduate from Iran. Is passionate about interventional radiology and artificial intelligence. He has a remarkable track record in research, imaging, computer-assisted diagnosis, business, and industry. He also has a wealth of experience in clinical practice and medical education. So he founded several startups and received the Innovation in Teaching Award from AME. Ali taught himself programming and has been a postdoctoral scholar at Mayo AI Lab since 2022. So as we can tell, he's going to give us some great information today, and I'm looking forward to it. So I will hand over the speaking to right now.
Thank you, Andrew, for your kind introduction. Andrew mentioned, I'm a medical doctor. I don't have any formal background in the computer science, but I participated once in a CS50, a course from Harvard. And also I taught myself a lot of programming languages like C, Java, and Python. So here it is. Let's talk today. Today's talk is about computer vision, how we can manipulate and open vision data in our Python language or in a notebook. So yeah, I think that's it. Let me share first my screen and open the notebook together. If anyone has a question, you can write it in the chats. Also, you can open up your microphone and ask it yourself. Here we go. Let's start with. Great. Anyone can you see my screen?
Yes.
Great. So for downloading the notebook, you can come to my GitHub repository by github.com, Magnuj workshops. And then after opening the medical visual data, you can click on Open in Colab. And finally, here it is. Click on Open in Colab. And finally, if you want to run the codes yourself, you can click on Copy to my drive, and then you can run your own codes. Let's start with the introduction about the topics that we want to talk to today. So we want today to talk about two main topics. One is visual data processing, and the second is medical imaging toolbox. Hopefully, the most majority of the content of this workshop goes to the first part, visual data processing, because most of you needs that. And also, I would talk briefly about medical image toolbox, because if you need in the future, you might need in the future to work on medical data, and most of them are very different than other data that you could see in other tasks. So let's start with visual data. For downloading the data and also working yourself, you can click on the first code cell. Here it is. It will copy all the data from the GitHub and then move it to the contents that you have here. And you can find the list of the data here. So yeah. Is anyone knows about image exactly how image what image made of what? Not too much. Each pixel has a number. Yes. And Sergio, could you explain why each pixel is a value between the 0 to 220 to 55 until Sergio writes it? So yes, as you mentioned correctly, each pixel is a combination of pixels, and each pixel has a value in it, a value between 0 and 255. We call it the intensity of that pixel. So let's imagine that you have a CSV file. Here is the CSV file if I want to open it up, as you can see. So there is a lot of columns, there is a lot of rows, and each row can have a value. And based on that values, you can have intensities. Imagine that each cell is a pixel, and each pixel can have a value in it. So if we ask uh, uh, a package, for example, like a pillow, to show those values in a manner that would be visualized, make it visualize for human eye, it would be something like that. Okay, the zeros will be black, as you can see here, and the 255 is the most or upper number that you can have. It would be the white. And why is that is zero between the 0 and 255? Because each pixel theoretically should have only 8 bits, and each bit can have only two values, 0 and 1. So 255 would be the maximum number that can occupy uh, in 8 bits. Okay. So with this background, we can go now. Yes, that's correct, Ilham Ali. So with that background, we can go now to colored image. Colored image is the same as the grayscale image that we have, but the difference is we have three channels here. So when you go to an image and make it like an array that we would do it next in the next cells, you can see each image has three dimensions. One would be height, the other one would be width, and the second is the channel. The channel means the number of images or the number of colors it has. So I mean, for a normal colored image that we have, uh, it would be a combination of three separated images, blue, green, and red. And by combining these three channels, you will see a colorful image. Okay. So yeah, imagine that it is a image that has a height of 512 pixel and width of 512 pixel. And yeah, that's it. Now let's dive into some packages that we can use in Python language for manipulating and opening up the images in our notebook or in our codes for visual processing. The first package that we want to talk about is Pillow. Pillow is a high-level library for image input and output and manipulation. It is based on C. It is very fast then. So you can open up a file by a snippet like this from pil import image, and then image.open sample the downloaded the files that you downloaded already, and then show it here. That's it. So as you can see in the notebook environment displaying Peel, Peel can show the images in the uh, notebook. Some libraries that we will talk today about that, doesn't support this option like Peel, and we might use Matplotlib for showing the images in the notebook. So here it is. Let's now convert this image to a NumPy array. Are you familiar with NumPy? Have you ever worked with NumPy before, guys? Okay, good. So yeah, we can use this image as an input and then use an array function to convert the image in the NumPy array. As you can see here, it will give you a tuple that the tuple has three variables. The first one is the height, the second is the width, and the third one is the channels of the image. Because it's a RGB image, so you would have three channels. In other words, we can have, so yeah. Now, by the help of NumPy arrays, we can separate the channels and show it in a different axis here with the help of Matplotlib. So if we use channel 0 and channel 1 and channel 2, we will see three different images that by combining these three channels, actually, we can have the main image that we saw earlier. You can also convert images to grayscale images by getting a mean value, an average value of all three channels. Here it is another example that you can see. So by using the mean function, you can get the average of all three axes, axis 1, 0, and 2, and then uh, convert it like an array and then show it here. So here it is. It's your grayscale image that you converted it with the help of Pillow. If you if we want to look at this grayscale image to see how many channels it have, you might see it has one channel or zero channel because it's only zero, so it doesn't have any value. The tuple doesn't have any third value. So it won't show you anything, and you could see that the image would be a 2D array only, which is the height is 667 and the width would be 1000. Any questions until now, guys? I assume nobody has a question. Okay, let's go. We can also use some prepared some functions that Pillow has it, like like rotation and flipping. So it has a definite functions rotating 180 and also 90 degrees. As you can see here, by calling image.rotate underline 19, you can 90, you can have a rotated image, or by flipping left right, you can have a flip of that raw image you have. There is a question from Rishab. Sorry for mispronunciation. So channels are numbers of the pixels present. The channels actually is an intensity. Uh, let's say it in another frame. So imagine each pixel has three values, a list of values or a tuple of values that has three numbers in it. So I'm talking about the RGB. So you might have a lot of channels. If you have RGB images that has three channels, so you might have only three values for each pixel in it. That each value in each pixel is a representative of one of the channels. I will show it in couple of cells. Here it is. So here, with the help of scikit image, that might be more understandable for you. Any other questions? Yes. Thank you for Aaron for this kind information. This is very good. So yeah, here it is. Here we go. So another function that we talked about is uh, was the flipping the images. So these are some capabilities that you could have with the help of Pillow. Unfortunately, we don't use a lot Pillow because Pillow is very limited. So most of image processings goes with another packages like scikit-image, as a part of scikit-learn, and also other type of images. Let's start with scikit for the second package that we want to talk about, scikit-image, or as a part of scikit-learn that you might be familiar with it. Scikit-image is the most Pythonic image processing library. It has a very familiar API, and you can use it for pre or post processing. Also, it has a lot of functions. It has a lot of templates that you might use it very easily. If you can see my search engine, let's go to scikit-image. Here is the gallery if you want to look at, and there is a lot of variables. There is a lot of functions and ready to use notebooks here. For example, contouring, for example, active contouring, finding an skeletonized or edge operators and everything else. Scikit-image is very good. Most of the image processing tasks has been done with the help of scikit-image. So feel free to go to the website, you read the documentations and also the templates. The advantage of using scikit-image is you don't, most of the time you don't need NumPy for finding the image, for reading the images. Scikit-image itself uses the NumPy and reads the images as a NumPy array, as you can see here. So you can see here, there is a list uh, that is equivalent to list of the number of the pixels in your image, and uh, each pixel or each list has a list in it. Each list array, each list item has a list in it that is representative of the channels that it has. So the image number 2 that we are using now as a sample has 4 channels, as you can see. Channel 1, 2, 3, and 4. As you can see, uh, uh, mm, because skimage reads the images as an array, we might need to use other packages like matplotlib to show the images like other images that we could see, or something like, oh, sorry, I forgot to run this one. Here we go. So here is the image shape. The height is 499. The width is 1000. And the channels are 4. Do you have any idea what is the channel for? In your human eye, all of them are, so this image is 3 channels, RGB. Great. Yes, that's correct. The channel 4 is the alpha channel, which is which controls the transparency of each pixels. Great. You do know a lot. Okay, let's go to let's manipulate the image that we have. We can get rid of the fourth channel, the transparency, and only get 3 values, which would be equivalent to red, green, and blue. So if we want to again show this image in a language that scikit-learn reads, so you can see each value would have only 3 values now. Each pixel would have only 3 values. Scikit-image also has a very good function, which we call it transform. And transform has a lot of functions in it, methods in it. Resize is one of the most useful one. You can resize each image by the number that you define. For example, we want to resize the image that we have, that the shape is 499, 1000 to a half of that image. So we can divide the height and width by 2 and then show the image here. So you could see the image would be resized in a half of that image, and the pixels would be the combination of previous pixels. I mean, it would be the mean or average of other pixels around that pixel. So it would resize it in a way that it would be very similar to the uh, original image that you showed here. So yeah, let's get the value range of the original image and also see and also get the value range of the new resized image. So the way that resize works in the scikit-image is to normalize all the data, all the values. Yes, there is a link. I can give it to you again. Thank you, everyone. And here it is. Okay. So, yes, as I was saying, the way that resize works here is to normalize all the pixel values and divide them by 255 to get a range something between between 0 and 1, And then when you ask to show it, it will show it, it will, you know, multiply it by 255 again to show it in a way that is understandable for human eye. Most of the visual processing tasks, we use normalization because I know in RGB image, in 2D images that we have, uh, the the maximum value that you could have would be 255. But when it goes to medical images, we might have different numbers. For example, in DICOM images that I will talk about it later today, the value mm, uh, it would be probable to have a value like 1000, 1800, something like that. So again, after resizing the image, do not forget, if you want to save it in a save the resized images, you need to again multiply uh, the normalized image to 255. Then it would be more easier for you to see it as a human. Here it is. There is a challenge that I prepared for you. So if you want to play with it, be my guest. You can play here, and then also you could see the answer here as well. The challenge is about cropping. You might need to find the center of the images and then find the values of 100 by 100 pixel from the center of the image and then crop a square of 100 pixel from the center of the images. So for the normalization, I will talk about normalization later in a DICOM images that when I want to talk about the DICOM images, because uh, in on that case, it would be more easier to understand why we want to normalize all the numbers between the 0 and 1. Also, if you want to do a task of a machine learning task or deep learning task, as an input, it would be easier for machine to uh, give it a convert it to a number between the 0 and 1. Okay. And why it is like 994.994, because uh, the maximum number, the maximum value that this image has, the maximum number it has, it probably it is 254, and this image doesn't have any pixel value with 255. So that's why the range that you could see here is not 1. It is 994. Okay. Let's move on to the next uh, topic that we want to talk about. The next topic is the padding. So by the padding, padding is very similar to cropping an image. Essentially, when you want to pad an image, you create a larger image, then fill that area, fill a larger image that you created with all zeros, I mean black, Then paste the original image that you have in all other pixels that you created. So with this information, now you might play with the practical challenge number 2, that is that requests from you to create a padding, create paths for the image of the 100 pixels. Here is the snippet that you might to fill it out, and also there is the answer if you want to see the answer. Yes, it's correct. The other strengths that scikit-learn image has is the rotation, because it has a lot of it has a definitive a defined method that you could use for rotating the images, adding the add paddings and everything else, or cropping everything. So here it is. You can import from the transform the rotate function or rotate method, and then ask that method to rotate the image by 45 degrees. Here it would be your image. It is easier than, definitely it is easier than working with Pillow. As I mentioned earlier, scikit-image also has a lot more capabilities like contour detection, contrast enhancement, labeling operations, and everything else. Feel free to go to the templates, see the gallery, and also read all the documentations that the scikit-image has. In my opinion, it is the most useful package that you could use in your computer vision task. We also have another package that sometimes we use it as a for medical image processing. It's OpenCV that you could import it with CV2. So it's also OpenCV again has been written on C, so it is very fast. It also works on video capture, uh, and also has object detection and face detection. It's the most you know useful package that you could see. It's very good actually, but in medical imaging in medical imaging processing, most of the time we don't use it because most of the images that we use, like DICOMs or Nifty, are not readable, or we don't need it actually to work with CV2. It depends on the task you're working in it, because we don't have face detection in medical imaging. So that's why that's one of the reasons that we don't use a lot. Or if we want to work on object detection, uh, we prefer to train a YOLO model on object detection rather than using CV2 and their defined functions, defined methods. Let's start with uh, another image number 3, to see uh, how we can open an image in CV2 or OpenCV. So with the method image read, you can open up an image, then you might need to convert the image that CV2 reads, because CV2 reads the images by uh, the order of channels of the blue, green, and red. So it is different than other uh, uh, image opening packages like Matplotlib and others. So it's better to first convert it in a way that is readable for others like Matplotlib by calling the method color BGR to RBG. So it would be then standardized, and then you can do a lot of things on it and find the channels in a standard order like others. So you can get the shape here with the help of CV2. And also, as you can see here, uh, uh, the CV2 reads the images like NumPy arrays that is very similar to scikit-learn that you saw before. So between the pillow and scikit-learn and CV2, you might understand that pillow reads the images as a pixel values, but CV2 and scikit-learn read the images as a NumPy array and convert it first in a NumPy array and then read it as a NumPy array. Also, CV2, there's a question. After using CV2 color BGR2 to RGB, can we still use that RGB order in OpenCV? Yes, that's correct. You can use it. So first, uh, when CV2 reads an image, it will convert it automatically to BGR. So that's why we need to convert it in a standard order by calling color to underline BGR to RGB. It would be the same, but by standardizing it, you are helping other packages that you are using or other libraries or other uh, you know pre uh, pre-trained models to work on a standard order. Yes, that's correct. It's just a default order of OpenCV and not the required order for OpenCV version. Yes, that is correct. Okay, let's go to resizing. Let's check the resizing and everything else. The resize function is very similar to the resize function that we saw in the scikit-learn. You can give every value that you want here and then ask the matplotlib to show it to you. Here it is. You converted it easily to the height of 200 and width of 400 with the three channels. And the image range is 0 to 52 to 255. Here it is. Also, CV2 has other methods. It has actually a lot of methods. It has more methods than every other image library that you could find in the internet. It's the most useful one and the most comprehensive one. So you might need it for a lot of tasks you are doing, specifically when you are working on videos. So you can also work with the rotate. Here it is. You can ask to rotate it in 90 degrees clockwise or counterclockwise. It's not very good at, it doesn't have any method, predefined method like scikit-learn that you could easily give the angle. So if you want to have a custom angle for rotating the images, you might need to define the function and then use that function to rotate the image. Here it is. You can convert it by uh, to a tuple, and then using that matrix, because as I mentioned, the CV2 read the images as a NumPy array, as a matrix. So you might find the center of the matrix and then rotate it by the angle that you give it. So here it is. By defining this function, the rotate image, you can easily rotate the images by the custom uh, angle that you could give. Also, you might need to convert the images to grayscale images. As you saw earlier, for example, for pillow, for converting the image, a three channel image to grayscale, we needed to get an average of all the channels and then convert it to grayscale. But scikit-learn and CV2 has a predefined method that you could easily call it. And based on that, it will convert the image easily to gray. Here it is the method. Color underline RGB to gray. You can see here the shape of the image changed. The shape of image previously had three channels, but now by converting it to gray, now it doesn't have any depth. It doesn't have any channels. So it's only a matrix of values, and each pixel is a number between 0 to 255. Here it is. In some cases, you might need to create a binary mask from the images, meaning to convert all pixels to either 0 or 1. You don't need to have any other values. You only want 0 and 1s. Why we might need that? Do you have any idea why we need this type of binarized image? It's almost correct. The the answer would be the segmentation, actually. We might need segmentation mask for the images that we have. So by the segmentation mask, or we can segment the area of interest. So by overlapping that your binarized image that you have, for example, you want to segment a person from an image, or you want to segment a tumor from an image. So you create a binarized image and then register that binarized image in the image that you have. So therefore, you will be able to train a deep learning or machine learning model with a segmentation mask that finds the area of interest. You could also use ROIs, region of interest, which is a bounding box around the region of interest. But most of the time, segmentation is better because bounding box might have some information that you don't need. But segmentation, specifically the precise segmentation, would give your model a precise area of interest, would give your model a precise area of interest for the training. Mm, not exactly like a edge detection, but edge detection can be done by help of segmentation as well. The edge detection is the difference between the two values. the difference, uh, a rapid change of difference in the pixel values. By that, you can find the uh, edges. But the segmentation is for finding only the area of interest that you like. For example, you might find the shadow here. You might find the reflection of the images in the water, and you want to give it to the a model for the training. Here it is. By binarizing the image, you could give this area to a model to find the reflections in the image. What is the difference between the normal threshold and adaptive threshold? I will talk about it in later. Okay. So finally, if you create your binarized image, you might need to uh, save it in the disk for using as a segmentation mask. Here it is. Okay, so yeah, sorry. I thought I will talking about thresholds in the next cells, but as you can see, I don't have anything, so I might to talk about it now. So the normal threshold is a threshold that you define uh, in a value. For example, you might need to create a threshold by 100 and uh, convert every pixel value to more than 100 to 1 and less than 100 to 0. The adaptive threshold is, as you can see in the name, is it will be adapted by the maximum uh, maximum value that you have. Uh, for example, in the medical images that we use Hounsfield units, we don't use pixel values. We use Hounsfield units, and the Hounsfield units unit can be more than 5,000. So by adapting value, we find the maximum number, and then uh, normalize all of them to a zero, between 0 and 1, and ask our threshold function to convert everything from above uh, for example 0.5 to 1, and then everything below the 0.5 to 0. That's the adaptive threshold. When do we choose normal threshold over an adaptive threshold? Ryan answered, I think when lighting is uneven, adaptive is better. Yes. In the normal images, yes, that's correct. In a medical imaging, because we would have different values, so we can use adaptive. The threshold are chosen to find the values of interest and then change it to 0 or 1, or I mean 0 or 255. So yes, you will create or you will change the pixel values to either of 0 or 255. I want to find a very good example from Scikit image for the thresholding. So you might be able to understand it better. Another example of thresholding is for segmentation, as I mentioned. Here it is, for example. Yes, you can customize your thresholds based on the color that you want. For example, you can create a binary mask only based on the blue color or a green color. Here it is. One of the best examples of the thresholding is here for object detection or separating the objects. Mask WDYM. I'm not very good at abbreviations, guys. So let's think about the videos. Oh, okay. What do you mean? Thank you. The mask, so the RAM means but the mask, the segmentation, the binarized image. So you might need the mask or the label or segmentation for finding the object or the region of interest that you have in the images. You will create a mask or segmentation or label for your images. And then by registering that mask in your image, you will find the instance that you might be interested or your model might be interested to learn about it. Okay, great. So let's go to the videos. The videos actually are created but sequentially showing the images one after the other one. So imagine that you have a video that has three pictures or has three images that shows those 30, 30 images in a second. So the frame per second or FPS for the video would be 30. So if you find an video that has a FPS equals to 30 or 60, it means that it shows you 30 images or 60 images in a second. So by this definition, you might be interested to, read or open the images as the open the videos as the images and go frame by frame and change the image to a grayscale or for binarizing it for anything else. So here it is. You can call a method video capture. Then you would be able to open video.mp4 and then you can change the values of the video, I mean the height and the weight by 100 to 100 to crop it and then create a new video. So by the help of CV2, you can resize the video. You can, change the video to grayscale, change the color, brightness, intensities, and other things that you might be interested. Image.io also is a very good library that you could open a video and process the video frame by frame. Any questions? The main thing that you should learn from this workshop is this one, that the that each image actually is a list of the pixels, list of the cells, that each pixel can have a value in it between 0 to 255. So the whole image processing and everything else is based on this image, or even edge detection, segmentation, and everything else. Okay, I assume nobody has any question. Let's go to medical imaging toolbox. You are familiar with PNG, JPG, and other type of images that is, usually everybody use that in the Windows, Linux, or Mac. But in the area of medical images, we uses other type of images. Mostly we use DICOM and NIFTY. The DICOM, or digital imaging and communication, is in medicine, is a format that we use that for keeping the patient information along with the image itself. So, and also as I mentioned before, in the medical imaging, we don't use RGB values, or we don't use pixel intensities. We use Hounsfield unit. The Hounsfield unit is the number of exposure that the detector in the CT scan or chest or X-ray machine, there is a detector and there is a source of the X-ray. So the Hounsfield unit is the number of exposure that every every part of detector got from the source. So based on that Hounsfield unit, which I recommend to read and learn about it, you can have DICOM images. And DICOM images has a lot of tags. Let's see here. So except that values, as I mentioned here, like these images, we have a lot of values that has the instance number, the series number, the patient position, the spacing between the slices. I mean, by CT scans, you have a lot of slices that each slice has some part of the body. Okay, so between those slices, there is a gap, and we call that gap slice thickness. And also, the spacing between the slices, these are the same. And also the patient position, you might find it because when a patient uh, goes through a CT scan device or chest X-ray device, they might have a lot of position, for example, standing, sitting, and everything else. So that's why they created DICOM, or which is abbreviation of digital imaging and communication in medicine. There is a lot of applications that you could open a DICOM image. One of the most important one that we use in medical imaging is 3D Slicer and ITK Snap. These two is easy to use. Also, Airphone View is very good, but we don't use it a lot. Also, you can go through all of the tags to find all the data about the patient. For example, if you want to know what is the name of the patient, or what is the thickness of the slices, for example, you want to find high quality or high resolution MRIs or high resolution CTs. So you might need to find the slice thickness of that CT, or a space between the slices. We use PyDICOM and Simple ITK for manipulating DICOM images and Nifty images. Here it is. By installing the pip install DICOM and importing it and also importing the matplotlib, you might be able to you know, open a DICOM image. The extension for DICOM image would be DCM. So there is an image here that you might be read it with the help of DICOM PyDICOM. Here it is, PyCom DCM read, and also show it with a matplotlib. Here is the chest X-ray of a woman, as you can see here. And as you could see here, the size of the shape of this image is 2020 something. Yes, I will show it later. So here it is, yeah. Also, you can see all the tags of the image that this image has. For example, the manufacturer is the GE Medical Systems, the physician name, manufacturer model, patient name, which is empty now because this is the identify, patient age, sex, birthday, if it is the identify or it is identified, focal spot, instance number, how many it means that how many images is in this DICOM. For example, if it's a CT scan, you might find 200 or more images in one series. I will talk about that. There's a question where we can find some sample patient images for data. I will talk about that later. So yes, the pixel data and everything else. Here it is. You can also find the exact value of the tag. So it would be very easy to, filter the images that you have based on the position of the patient, based on the values of the patient and everything else. Also, you can search through the DICOM tags and find your interested tags. For example, you can find every tag that has PAT in it. So you might see the distance source to patient, the patient age, patient sex, and everything else. The problem that we have with the DICOM is most of them are too big. I mean, each DICOM won't be more than 3 megabytes. But if you want to have a CT scan, you might have more than 200 DICOM images that you might, make it a zip or something else to move it from a server to another server for image processing. And also, it has a lot of data that is very important, and according to Health Insurance Portability and Accountability Act, or HIPAA, each image should be de-identified to move it to another person. So that's why we use most of the time Nifty. The Nifty, excuse me, the Nifty is very flexible. For each series, it would be only one Nifty. A Nifty actually is a NumPy array, so it would be more, it would have smaller sizes, and also because it's only arrays, it would be more easier for AI algorithms or other Python libraries to read and manipulate than DICOM data. The way that we convert DICOM images to Nifty is different things. One of the best one that I am using is DICOM to NIX. which is, in my opinion, which is the best. So feel free to read the DICOM to NICS. Here it is. If you search about it, DICOM to NICS. It has a very good documentation, how to download the releases, and also how to convert a folder of DICOM images to a Nifty files. Here it is. So, but for the sake of this workshop, let's manipulate the only DICOM that we have with a simple ITK and knee bubble. Knee bubble is the library that will read and manipulate Nifty images. And also NumPy. With the NumPy, you can also open the Nifty images and manipulate it as you want. Here it is. Let's install these packages and then go through the code. So, for example, we want to get the list of the DICOM images that we have, and then based on each of them, open a writing object and convert them to a Nifty file. Here it is. We got sample DICOM image and then convert it to Nifty here. You can also open a Nifty file. Most of the Nifty file, we use gzip for that to make it more smaller. We don't need to the real Nifty one most of the time, so it would be very easier for us to convert it to gzip file and move it along the servers. And also most of the algorithms like knee bubble, like NNUnit, I mean, they use Nifty gzip files. So here it is. For example, let's go through the tags. Let's go just through the tags of the Nifty to see how many tags we have. Yes. You know, when you convert, there's a question. It is just the metadata that you lose when you converting to Nifty. Yes, we only lose the identified data when we convert the images, DICOM images to Nifty. But in other hand, we would have a stacked images that is easier to process because it will convert it to NumPy arrays. So it will stack all other the DICOM images. For example, for one CT scan, it could be more than 500 images. So it will convert it to NumPy and then stack all of them together and give it to you only one file, which is smaller than the DICOM images that you have, which is de-identified and which is very easier to understand. Because if you want to, for example, read the DICOM image, you need to have the number of the tag that you want to find. It's very hard to have all the tags. I know you can search through that and also based on that get the values, but most of the time it's very slow to read the tags in the DICOM with the help of PyDICOM. So by converting the images to Nifty, it would be easier to read the image and also easier to find the tags and also filter the images based on the tag. For example, imagine that you want, uh, for example, one of the tasks that I'm working on is the MRIs that is only in a sagittal view. There's different views in the body. So if you go from for example, the left side to the right side, image by image, we call it sagittal view. Let's see. MRI sagittal view. That's the sagittal view coming from the left side to the right side. So there is a tag for finding the sagittal views in the Nifty. So if you have a bunch of data that is very, you know, uh, that is have coronal, axial, or sagittal data, so you would easily filter the data based on the tags of the Nifty. Or, for example, you have a task that you want to find only coronal view. The coronal view means uh, you move image by image from the anterior to the posterior, from the front to the back. So that's the coronal view that we could easily use it. Or also the angle and also the rotation of the images. So by these pixim tags, you might be able to find the exact angle and also the rotation of the images. And by manipulating the pixim images, you would easily convert the images in an angle or normalize all the images in a zero angle. That would be very easier for your machine to learn or inference to do inference on it. That's why most of the time we use Nifty. Here it is. For example, you want to find the affine. I mean by the affine, you might find the 3D dimension of the images and then change the affine in a way that you want it. For example, you want to change the affine or re-slice the images. I mean by re-slicing, converting a coronal image, for example, to a sagittal view. So you will again change the matrix in a way, the matrix are from anterior or front to the back. So with the help of affine and the Nifty, you can again create a 3D dimensional data and then re-slice it again in sagittal view or going from left to right. This is why we use Nifty images, because in the DICOM image, you cannot do this type of pre-processing. But with the help of the uh, Nifty, you can easily change the angle, rotation, and also uh, uh, change the slices from coronal or axial or sagittal to each other. Most of the Nifties that we use is 3D images. That would be easier for us to understand it in a 3D way. Or if you want to do a 3D segmentation, or if you want to do a 3D object detection, it's very good to convert your images to Nifty. But the data set that you mentioned, for example, in Kaggle or RSNA, which is the data set, most of them are in Kaggle again. And also Amy Stanford. In chest X-ray images, it's better to convert them to a 2D images like PNGs or JPEG images and everything else, not Nifty, because the Nifty is, it's not very useful for 2D images. We don't use it. We either of using DICOM images itself or convert it to PNG. That would be easier for process because the size would be smaller and it would be easier to, process it uh, with a mesh. So here it is. If you want to convert a DICOM image to a 2D image, you first need to normalize the image. Why we need that? Because as I mentioned before, we have a unit which we call it Hansfield unit. The Hansfield unit is the number of exposure of that detector detected from the source of the X-ray. Okay, so for example, as you can see here, the maximum exposure or the maximum Hus field unit that you could see in this image is 15,000 Hus field unit, HU, which is way more than 255 we normally have in a bitmap or JPEG, I mean, JPEG or BMP images that we have. So for the sake of conversion of the DCM image or DICOM image to the bitmap formats, we need first to normalize everything and by the maximum number, and then here it is, by the maximum number to create a value between 0 and 1, and then by multiplying it to 255, we could have a bitmap images. Here it is. You could also change an Nifty image to a 2D images or bitmap unit with the same function. You will get the maximum number and then convert everything to 255. Here it is. It's almost the same. Let's see. It is not this one. Here it is. That's the images we converted from Nifty to a 2D image. Finally, there is a third challenge that you might be interested to solve it. The third challenge is to read all files and go through it one by one, convert all images to 3 channels, and resize the images in a way such the aspect ratio is not changed. Add a padding, and then save all of them as a PNG format in the new sample folder. You might need to create a new sample folder as well. Also, there is a answer if you want to check it out. Robert also asked about the no, sorry. Ryan asked about some data set that you could find patient data. So RSNA or Radiological Society of North America, I think. I misspelled the Kaggle, sorry. Uh, uh, is very good because every year RSNA has a challenge. You might go to the Kaggle page and find the RSNA's Kaggle, and you might find a lot of images. Also, if you are interested to work on pathological images, you could also go to Kaggle and search about pathological images or pathological uh, uh, data sets. AMI in Stanford or Artificial Intelligence Medicine something Stanford is one of the good centers that provides a lot of medical data that you could easily download those data and also work on it. For example, Shakespeare that has I think more than 20,000 images, 20,000 chest X-rays is from AMI Stanford. You might go through the data sets and also download all of them and work on whatever task you might like to do. Looking also in GitHub would be very good because in GitHub you might find a lot of code snippets on these datasets that I mentioned. Okay. That is all from today. Any questions?
Okay, I'm monitoring the chat. Doesn't seem like anyone's asking anything. I'll just give you all a couple more minutes here.
Great.
Okay, well, if there's yeah, that's true. It can be hard to come up with some questions when you just learned so much. Um, okay, but well, everyone has a chance to be asking their questions. So next session is on Sunday. And what's going to be happening is we're going to be learning how to build an image classification tool. So I hope to see you all there. It's going to be very exciting. And yeah, I'm seeing a lot of thank yous and questions. Okay, well, in that case, everyone have a great evening. And thank you so
Thank you,
much,
everyone.
Dr. Ali. That was a really great workshop.
Of course, thank you for inviting me. I hope everyone has a good time. And also, I try to, excuse me, I try to have some introduction about the medical imaging, which is very important for us. So as I mentioned for you, we use Nifty a lot. We use also scikit image a lot. So if you want to work on a classification or segmentation algorithms in the future in the field of medical imaging, you might be interested to learn more about how to convert DICOMs to Nifties, how to process it, and also how to create binary masks for in Nifties, and finally how to use scikit image and converting Nifty to MPRS, which is uh, right now is MPRS. There is no conversion, so how to load it in a scikit image and use it those templates in the scikit image for uh, some pre and post processing.
Oh,
Feel free if you want to contact me, you can search my name in the Mayo Clinic and here it is. Thank you, everyone. Thank you, Andrew.
yeah, thank you again. That was amazing. Have a good night, everybody.